Club has I'll start over. Good evening, everyone. Welcome to the uh, club meeting here for February. Um, how this all started out was at the last field day. The club has a high gain TH3 tri-band Yagi that we've been using, I don't know, for many, many years, and it's always worked great. So last year it's stored in my barn, and I just cart it over to field day every year, and George and Connor are experts at assembling it now. So they put it together. We put it on the 30-foot U.S. tower mast and cranked that puppy up and went to test it, and blah, it was terrible. It, SWR was nowhere to be seen on the bands, just a mess. And so we cranked it back down and quick ohm-meter check of a couple of the traps, and they looked like they were open, and the trap should be a short because it's an inductor in series. So they said, something going on here. So we quickly went to Plan B, and luckily we had a dipole, and we were able to put that up and use that on multiple bands, and everything worked out fine. But so I took the beam back home, and I was given the marching orders that you need to go through the beam and see what's what. And I said, yeah, no problem. I can take the traps off and test them. And I don't remember who it was, but somebody said, testing traps. That sounds interesting. I don't know how to do that. Would you be willing to do a presentation for the radio club about how do you test the traps? So that's what we're going to do today. All right. Let me share my screen. And there we go. Okay. I think everybody can see that. Good. That works good. All right. So antenna traps, what they are and how they work. So let me move this Zoom screen here so I can see what I'm supposed to be talking about. Okay, that's better. All right, so antenna trap is something that gets added to an antenna, and it turns a single band antenna into a multi-band. Like the name implies, the trap stops or traps the RF energy along the wire or, you know, aluminum tubing or whatever along at the trap location at the trap resonant frequency. And you'll hear more about that in upcoming slides here. But, typically antennas that we use are half wavelength dipole type antennas. And even on a Yagi, that's basically what they are. And so the length of the antenna at a half wavelength is tuned for that band, but it only works for that band. And so if you want multiple bands, you have to do something else. You either need multiple wires, or you'll see here how the traps allow you to do that with just the single wire or tubing on each side. Okay, why won't this move? There we go. So you can think of the trap as a switch in the antenna conductor or wire that operates at a specific frequency. At the resonant frequency of the trap, the switch looks like an open. At the non-resonant frequencies of the trap, other frequencies, the switch looks like it's closed. So a trap is made up of a parallel LC circuit from a capacitor and an inductor. The resonant frequency of the LC circuit is given by 1 over 2 pi square root of LC. That's how you calculate what the resonant frequency of the trap. You take the inductance and the capacitance value, you put it into that formula, and it tells you what the resonant frequency is. Now, resonance, by definition, is defined at the frequency where the resultant reactance is 0. And that happens when you pick a frequency and a inductance value and capacitive value such that the inductive reactance and the capacitive reactance are equal. If you think about it, and you remember when you had two resistors in parallel, how did you calculate the equivalent resistance, right? Well, you can do the 1 over 1 over thing, but with two, you can also do the product over the sum, right? And so if you have your value of X of L and X of C, that's the two components in parallel now. They're not resistors, but they're inductor and a capacitor. And if you put that into the formula, you have X of L times X of C on the top, and then you have X of L plus X of C on the bottom. But the thing that's important here is you can't treat the X of L and the X of C as just normal numbers. In mathematics, these are called vectors. And what is meant by a vector is the unit has a strength or a magnitude, but it also has a time sequence or direction to it. And it just so happens that the X sub L and the X sub C are completely opposite to each other. They occur at opposite times, and you can think of them as vectors in opposite directions. So when you have two vectors in opposite directions and you add them together, they cancel each other out. So the resultant is 0. So that's why at resonance, the resultant reactance is 0, because the X sub L and the X sub C cancels that out. And to understand what's going on here, you can kind of think of the mechanical analogy of a pendulum and like a grandfather clock. Have you ever thought about why that works and why that keeps going back and forth? So what happens with a pendulum is you have a mass, right? And if you take that mass and you raise it to some level, you've given it what's called potential energy, because gravity will then, when you let it go, make it do work. That's called potential energy. As that mass goes through, and when it hits the very bottom, it's traveling at its maximum velocity. So that's called like kinetic energy or angular energy, right? And so what's happening there with that pendulum is the energy is swapping back and forth between the potential energy and the angular energy. And if there was no losses in the bearing and the friction from where that thing swings, that thing would swing forever. If there was no wind resistance because it had to cut through the wind, right? That thing would just swing forever. And those two energy things would just keep swapping back and forth between potential and kinetic or, velocity and energy. And that's exactly what happens in the electronic circuit. The energy, when voltage is applied to an inductor, a magnetic field is created, and the energy is stored in the magnetic field. When voltage is applied to a capacitor, an electric field is formed between the two metal plates through the dielectric, and energy is stored in the electric field. And it just so happens the time at which those energies are maximum when they're stored is exactly opposite. So in an LC circuit, once you excite the circuit, what's happening is the energy in the inductor magnetic field is then swapping over to the energy in the capacitor electric field, and that goes back and forth and back and forth and back and forth in that little circuit, right? The energy just flows back and forth. And if there was no losses in the circuit, if we had an ideal capacitor and an ideal inductor, no losses in the resistance of the wire and loss in the dielectric material between the capacitor plates, that oscillation would happen forever, right? But of course, in the real world, there's no such thing. So the oscillation happens, and then eventually, if you don't excite it again, it dampens out. Okay? Does that make sense? So that's what a trap is. Oh, and then one thing. Um, so when you do that calculation over the product of the sum, you've got x sub l times x sub c divided by 0, because the x sub l and the x sub c, when you add them, two vectors together, you get 0, right? Well, what is the impedance of something if the denominator in the equation is 0, right? Is infinite, basically, right? So that's why the impedance of a trap at resonance is very high. Well, yeah, it's approaching infinity, I should say. Yes, yes. Right. Theoretically, it's undefined, right? Right, yes. But it's very high, approaching infinity. In a real circuit, because of losses, it's not infinite, but it's very, very high. And that's how the trapping works, right? And that's why it looks like an open switch. What's an open switch? That's a very high impedance, right? Open circuit. So that's how the trap works. But it works automatically when it sees a certain frequency. That's the whole nice thing about it. You don't have to go up there and close the switch. So what does a trap look like? Well, you can make one. You can take an insulator and wrap some wire around it to make a coil, and then put a capacitor in parallel with it. So there's um, nothing magic about making a trap. You can make it, of course. It's going to be outside. You need to make it, waterproof and all that kind of stuff. But you can make trap. You can even make traps out of winding coax, actually, and use the winding of the coax, the shield, winding the shield as the inductor, and then the capacitance between the center conductor and the shield acts as the capacitor of the parallel circuit. So you can actually make traps out of just a piece of coax and winding it on a form. So here's just a couple examples of antennas where we use traps, and probably the most obvious one is the top one, the conventional uh, 80-40 meter dipole. So you have a trap, and so you'll notice that the trap is placed um, so that you have so you've got 31.1 feet on each side, and so that's what 62 feet. A half wavelength on 40 meters is like 64, 66 feet. And there's a little bit of loading that the trap adds, so that's why the wires are a little bit shorter than the exact half wavelength, which would be more like 66 feet. But when you excite this with 7 megahertz, the trap looks like an open circuit. So all the antenna sees is those two pieces of 31.1 foot wire, and it resonates on 40 meters. When you excite the antenna with 3.5 megahertz, now the traps are no longer resonance. It sees the entire length of the wire, including going through the trap, which adds a little bit of loading, and you see that you have close to the 130 some odd feet you need for an 80 meter dipole. So, and then the other one below it is kind of a offshoot of that, and they fooled around with the lengths and made it so it'll work on more bands than just the 80-40. And so the equivalent circuit of a trap in real life, because yeah, it's a parallel LC circuit, but we're not dealing with ideal components. There is some resistance. And so you can model the trap one of two ways. You can model it as uh, up top there, where you have a series resistor in series with the inductor, and model it circuit wise that way. Most of the resistance associated with the trap comes from the inductor and not the capacitor. So that's not a bad model. The other way to do it, though, is just take the parallel LC circuit and then model a parallel resistance in parallel with that to account for the resistance that's in the non-ideal components. So how are we going to test the trap? Right. Well, we're going to take advantage of newer technology that we have today. And I should have brought I didn't think to bring it. I should have brought it. But before we had all this newer technology, the way we tested traps was there's something called a grid dip meter. It's a vacuum tube device, and it's essentially an oscillator where the coil part of the oscillator circuit is exposed, and you can take that coil and you can put it near other LC circuits. And when the LC circuit that you're putting it near to, its resonance, it draws power away from the oscillator in the grid dip meter and causes a dip in the grid current because you're pulling power away. And so there's a meter on it. And what you do is you put that near the trap and you tune the dial. And it had just an analog dial. You tune the dial and you'd look for the dip, find the minimum, and then you go read the dial, and that would tell you what the resonant frequency of the trap was. It worked. Was it exact as what we're going to do here? No. Here you can actually see you know, the filter action of the trap and how much of how many dB notch it provides and so forth, and probably much more accurate frequency measurement because we have a, synthesized signal source in there, but the old way would work. But I thought I would show you how you do it today with the device called the Nano VNA. And the VNA stands for Vector Network Analyzer. And what it does basically is it measures signals either reflected or passing through a network. Some of you are probably familiar with the antenna analyzers. MFJ had them for a long time, the 259 and so forth. And today it seems like the rig experts are the biggest one out that everybody has. So those are kind of like network analyzers. They're really called antenna analyzers, but they're what's called a one-port analyzer. It only has one connector on it. It sends a signal out and then looks for the reflected signal coming back. You can do the exact same thing with the Nano VNA here. You just use one of the two ports that it has, and you can do the exact same thing. The advantage of the Nano VNA, it is actually a two-port network analyzer. So you can send a signal out, send it through a device, and then measure the signal on the output of the device coming back. So you can measure things like amplifiers, filters. A transmission line is a two-port network. A trap is a two-port network. It has two sides, right? So anything with two connections or two ports would be considered a two-port network. And that's the advantage of the Nano VNA. Not to mention its measurements are much more accurate than the rig experts. I mean, the rig expert stuff are fine, especially for, amateur use and what we're trying to do. But this is actually more accurate because before you use the instrument, it comes with what's called a calibration kit, little SMA connectors here. And it's called an SOLT calibration kit, and that stands for short open load through, right? And so what you're doing is you're putting ideal impedances on the analyzer. It's saying, okay, that is supposed to be an ideal open or short or 50 ohms. Here is what I'm measuring on the analyzer. Any instrument, there's always some instrumentation error in the measurement. It measures that error difference from what an ideal one should be and stores that away in a calibration table. And then when you go to do your measurement, it uses that error correction to correct the measurement, so it's going to be looking like it's ideal. And that really gives you a much more accurate measurement. Is it totally necessary for like most antenna measurements? No. But if you're measuring more detailed circuits, then this is the way to go. The other advantage is, some of the rig expert things are like $200, $300, $400, right? I mean, I've seen them up to $1,200 for. So this is $80. So not only is it something us frugal hams can understand, it takes a little while to get to use it because it's maybe not quite as user friendly. But if you have one and you're interested, I developed a step-by-step procedure. I have a little document that I can send to you, and it tells you exactly what to do so that you can do the same thing you would do with a rig expert. It'll do a lot more, but at least the step-by-step thing will get you to, yeah, I can do, look at the SWR as a function of frequency and see, what my antenna is doing and so forth. So here's what's inside that nano VNA. You have a microprocessor. That's the STM32, and then down on the bottom there, just to the left of that, is the synthesizer. And then there's a digital display readout. The TLV 320 thing, that is a analog to digital converter. There's a set of mixers, 3 mixers, that down convert the RF energy into lower frequency that the digitizer can digitize and turn into ones and zeros, so the microprocessor can then do its magic with that. And then there's a directional bridge up at the top. That bridge separates the forward and reflected power. So it allows a way for the instrument to look and differentiate the power going out from the power coming back. So I put together a little animated example here of what we're going to do in this measurement is called a transmission measurement, or sometimes a through measurement, because we want to measure the energy going through the trap. Okay. In engineering circles, there's something called S parameters, and that would be called S21 for those who know what that means. But just think of it as energy going through. And so what happens is the microprocessor commands the synthesizer, and it puts out RF energy at a particular frequency, and that RF energy is sent up to the directional bridge. The synthesizer has a second channel, and it also puts out another frequency called the local oscillator frequency that's slightly offset from the original RF frequency. And this is needed, the local oscillator is needed to drive the second port of the mixers, and we'll get into that in a little bit. The second channel of the A to D takes that RF signal, samples it across through the mixer, and that goes into IN2 of the analog to digital converter, and that's your reference. That gives the uh, A to D and the microprocessor a reference of the signal that you're sending out to the bridge. That signal goes up to the bridge and then goes out port one of the uh, network analyzer, often called the transmit port, because that's the signal going out. If you have a device under test, that's what the DUT means. In this case, our device under test would be our trap connected between port one and port two. Then the signal goes through the device under test, comes out of the device under test, and goes back into now channel one of the uh, analog to digital converter. It gets down converted to a lower frequency, and then the A to D digitizes that. And so what the microprocessor does then is it looks at the strength of that output signal and compares it to what we sent on the input. And if you take output versus input, you can calculate gain, insertion loss, right? If it's like an attenuator or a filter or something, it's going to have some loss. But if it's an amplifier, then it would be gain. But it can measure the difference between the signal going into your device under test and the signal coming out of your device under test. And then it does this for every frequency. The analyzer has 1,001 digitized points. And so it's doing this for every frequency between the start and stop frequency that I set up on the analyzer. And it gives you a nice graph. You can look at the graph and so forth. So any questions on any of that? No, you can't do it while the antenna's in the air. You would have to take the trap out part. Yes. Yeah. Yep. Yeah. There's no way to do it, unfortunately, in the air. So here's what we have set up. And in fact, a better picture is that. That's what we have set up. We're going to take the nano VNA, channel 0 TX channel, and the channel 1, the RX channel, and connect it to the trap. And the way I did that is I picked up some SMA to banana jack cables. And so what I'm going to do is take the trap and connect the red alligator clip to one side of the trap, and then take the other red alligator clip and connect it to the other side of the trap. So now we've got the center conductor of the coaxes going through the trap. And just so that we complete the ground connections, I'm going to connect across with another little cable here, the two black ground connections. Okay, so we should be all connected up. So now I've got the Nano VNA connected to my laptop using a USB cable. I've calibrated the Nano VNA just before coming here to not take up time in the meeting, putting the open short load and through connections on. I did the calibration ahead of time and stored it in the little instrument just to save a little time. I've set the Nano VNA up for the through mode, the S21 insertion loss mode, and set the display to read what's called log magnitude. It will, and if the trap is working properly, we should see a large insertion loss at the trap frequency. So what I'm using to look at the Nano VNA with the laptop, there's a couple different software programs that are available, and these are free. You can get them online. One's called Nano VNA Saver, and the other one is called the Nano VNA app. I happen to have the Nano VNA app software on my laptop, so that's what we're going to use. Okay, so now let's test the trap. I've done all the connections that are talked about there, connecting the trap into the cables and so forth. And so let's see about testing the trap. See if I can share the Nano VNA Saver software here. Hold on a minute. I don't know why that's different from what I normally see. Let me minimize the Zoom thing here. Okay. And now let me share this. Always cockpit errors here when you're trying to make this all work. Okay, good. So you see the screen that I'm sharing now. So first thing you need to do is to connect to the Nano VNA. You see it says disconnected. I've selected COM port 3, and hopefully when I hit this, it will connect, which it looks like it did. And I've got it set up. So I'm sweeping over the whole HF band, 3 to 30 megahertz, and set up with everything should be okay. So now if I just go up here and can do a single sweep or continuous sweep, I might as well do a continuous sweep. Oh, it disconnected again. Okay. Why did you do that? Nope. Doesn't like it. Huh? Let me try. Let me try a different COM port. I don't know.
Next month's presentation will be on troubleshooting your Nano VNA.
Yeah. No, it's not the Nano VNA. It's the software. It's always those software guys, you know. Yeah, piece of data. Great.
Quick, hit the button before it disconnects. Yeah. There it goes.
Okay. So now you're seeing the. I mean, it is a little squirrely here because we're using long leads and stuff, but you can see the resonant frequency of the trap, and I can bring the cursor over here, and you see it's um, I turn on. Oh, I got to turn on info. That's what it is. and the cursor again. And you see that the trap frequency is 21 point something or other megahertz. So this is a good 15-meter trap. This trap is working. Should be nothing wrong with it. My job is to now go through the other plethora of traps in the antenna and make sure they all work. I'm sure I'm gonna. Well, we measured a couple that looked like they were open, so there's got to be some bad ones in there. I just haven't done it yet, but I'm I'm doing it one trap at a time and then putting it back so I don't have to go and adjust all the lengths again. Yeah, right. We got 4 months, so anyways, that's how you test the trap, and it works really well. You see I don't know, when you're reading about 45 dB of insertion loss there, that's quite a bit, quite a bit. By the way, if anybody's interested in these slides, you're welcome to it. Send me an email, my call sign at comcast.net, and I'll be glad to send you a PDF file of the slides if they're interesting. All right, I think. Let me just check and see if there was anything left in the presentation. I don't think so, but
Greg, what's some of the most common failure modes? I mean, you said
oh, with
open,
traps,
yeah, and the traps. What's the most common failure modes?
spiders. No, believe it or not, yeah, spiders get in there and they get webs but condensation. A lot of the time, what happens is condensation's gotten in there, and then connection joints have oxidized. So you got to take the connections apart, clean them up, and put them back together again, shine everything up, and then everything usually. I mean, they're not complicated, right? I mean, there's nothing really in the adductor that could fail. You could have a capacitor go bad, and then you'd have to replace it. But uh, most of the ones that I've worked on were either corroded connections or spiders. What's that? Yeah, loosen up. Yeah, all corroded. Yep, yep, yep. Let me just see if there was anything. I think that was probably the last slide, but let me just. Yeah, that was it. So once again, uh, if you think of something down the road that you said, "Oh, geez, I should have asked that question," you can just shoot me an email, or if you would like a copy of the presentation, I'd be more than glad to send it off to you. So, thank you very much.